Okay, so I think we are live. So yeah, welcome everyone to Spatial Spotlight. This is the series of short videos that we do live on LinkedIn in CARTO every week. And this week's is a short one, but I'm going to be presenting you a little bit on our new functionality of Composite Spatial Scores in Snowflake. That's why we have the worksheet here ready. So first of all, I'm Diego Vicente. I'm a data scientist at CARTO. And yeah, let's go for it. So we have released recently this functionality in Snowflake, even though we had it in BigQuery before. So we have been working hard on it, and now it's ready for you for us to show you. The use case we have today, it's going to be a very simple one. We have basically a set of variables that are related to biking in Madrid, and we want to have a measure of how friendly different zones in Madrid are related to those variables. So ideally, what we want to have is an actionable KPI that we can use to compare different zones. We can aggregate, we can interpret. But right now, what we have is a set of variables. I can actually show you here in the table. Let's see. So basically, we have an H3 grid. It's resolution 10. So it's going to be a good resolution for a city. And we have several columns. Basically, the lane rate, it's a measurement. It's basically kind of a weighted average of meters depending on the types of lanes dedicated for bikes that are in the cell, which is a really weird and complex measurement. But it's basically related to the kind of lane, that is, if it's a dedicated bike lane, if it's a shared lane, if it's a quiet street, which is also contained in the open data of the city hall. We weight how those are like bike friendly, and then we multiply and aggregate the meters. So not only how dedicated to bikes are is important for this measurement, it's also the amount of meters. The more lanes in the cell, the highest the number is. The thing is that it's kind of hard to compare, so I'm just going to show you a map so you can take a look at it. This is how it looks like. For people that know Madrid, you can probably see some like familiar shapes in it. Um, but yeah, the higher the measurement, the more dedicated, the highest the investment on bikes on the area is. But this is not like by itself super informative. So we wanted to compare to other variables. For example, um, the walking distance to a parking spot for bikes. We have computed for each of the bike parkings, public bike parkings that are in the city, the distance that we have 5 minutes walking and 10 minutes walking. This is using the isolant functionality in CARTO. And with those isolants, we compute what's the area that it's covered by the isolants for a cell. So if I show you the map, this is going to be much easier. We can see that we have the two measurements for 5 minutes on the left and for 10 minutes on the right. 10 minutes is like a good deal of the city it's covered by it. And then on the 5 minutes walking, we can see that it's more spotty. But yeah, for example, when we have 100% coverage, is that for any point of the cell, you can get to a bike parking by walking 5 or 10 minutes. If we have a 50%, is that half of the area is covered by those walking distances, and if we have a 0%, is that there's no bike parking at 5 or 10 minutes walking. So yeah, this is yet another variable that we can use to estimate this, but it's not by itself super useful. And we also have another one that is the elevation difference. This is basically the difference of the lowest altitude and the highest altitude within a cell. And I really like this map. I think that this looks awesome. And you can see how not flat is Madrid. Again, for everyone that is familiar with the city, you can see that it's really not flat, especially because the river in the middle has like these two slopes on each side of the city. So yeah, in this map we can see how the stronger the color, the steeper the walk is on a cell, and that is also related to how friendly each zone is to biking. Flatter areas are easier to bike than steeper areas, so we can also take that into account. But again, just like using this information, we have like these three maps, but we cannot merge them together by themselves. We can try to compute something, but we have to devise a method to it. But now we can simply use the spatial composite scores. So I'm going to show you three methods that we found to do this. I'm not going to dwell too much on the syntax, but just for everyone to get a grasp on what we can do. We can use the unsupervised method when we simply want to input variables and then get an index. It's basically consolidating all the variables. The method by default, what I would recommend to start with is the entropy one. This is basically autopilot on computing the scores. You just input the variables and it's going to check how many information each one provides, and then it's going to consolidate it into a single measurement. We can also expect the return range. So in this case, we will get a measurement from 0 to 1, and the input query, it's simply just taking all the variables except the elevation, which we are multiplying by -1 because the sign is important for the scores. In this case, the higher the elevation difference, the steeper a cell is, and the less friendly is for the index. So we want it to contribute in a negative way. So we can just multiply by -1 and flip the sign. And so now it's diminishing the index instead of contributing to it. So yeah, we can just take a look at what it looks. So now we have the friendliness index. We can see how the city center is mostly friendly. But then we have like some areas here, which is Casa de Campo, which is like this kind of country part that is in this area doesn't look like too friendly, even though it arguably is. So we can, if we are not happy with the result, we can tweak it with the knowledge we have. For that, we have another method within the unsupervised index, which is the custom weights. When we use custom weights, we can provide for each of the variables that we are giving to the index a custom weight. So, for example, to get more friendliness in Casa de Campo, we can simply have a higher weight in lane rate, which measures the meters of dedicated bike lanes, and then to the distance to a parking, and just reduce a lot the elevation difference. For the rest, it looks pretty much the same. But when we compare the original index, the entropy one, with the custom weights, we can see how this part in Casacampo that is next to the river now has like the appropriate amount. And we can see also how the neighborhoods outside the city center have pretty much higher concentration of the index. So yeah, this is like a way to control what the index is returning. And then we can go even a step further. So for example, if we use the supervised method, we are going to train a model and then use the predictions of the model as a measure of how the variables are explaining this variable that we are inputting. And the index is going to be how the actual amount drifts for what the model expects. So basically, those areas that have a higher value than the model is expecting, we have a higher index. And those with lower values than expected, we have a lower index. So it's zero-centered. If the area has exactly the values that we are expecting, it's going to be centered in 0. And to do so, we are going to compare it with the accident. First, what we do is take the amount of accidents and just have a quick computation that is going to add together all the accidents around the cell. That is, it's going to take the accidents within that cell and the k-ring of radius 1 that is around it, and add it together. So for example, if we have an accident in a cell and another accident in a neighboring cell, each of them are going to get 2 accidents. This is going to smooth a bit the index, not to have like too harsh, and it's going to provide more samples because to do this, we are only going to take into account the cells that have accidents. We don't have to do this, but it's probably going to be more informative if we only take into account those with accidents. And yeah, this pretty much looks the same. We are simply adding the accident count, but now we are calling the supervised index, and we are telling the model to predict the accident count, which is the variable that we just computed. And now the options are a bit more intricate. You can check this in the SQL reference because it's going to be much easier than just watching a video about it. But basically, we have 3 possible steps: an encoding step that we're not going to use because we have no categorical variables, and scalar step that is going to normalize all variables. We are going to use a min-max scalar. And this uses Snowflake ML, Snowpark ML actually, which is the Python interface that mimics scikit-learn. So everything is going to be more or less familiar to you if you use it in Python. And then we simply we are going to use a random forest regressor using the absolute error. And finally, we can also set a threshold that is going to return an error if our model is not good enough. We're not going to be setting a very high standard for this because this is mostly a toy example. But yeah, we can simply run this and we can see how now we have like this diverging index. We have those hotspots where there are like more accidents that the model would expect based on the variables that we are inputting. But we also have like these cold spots that have negative spatial scores that basically tells us that, well, based on the variables, we will expect more accidents, but we have less than we would expect. And yeah, this is basically it. It has been super quick, but well, we have seen 3 different ways of generating this composites index. And in case you have any questions or any doubts, you can refer to the SQL reference, but I'm also going to be checking the comments later. So please let me any comments with any doubts and questions, and hope we can address it together. So yeah, thanks for joining, and see you soon.